Hi, my name is Taylor Lukasic, and I will be demonstrating the properties of inertia through the tablecloth trick. We use the property of inertia to pull off this trick without breaking a single plate. The secret to this trick is Sir Isaac Newton's first law of motion, based on Galileo's concept of inertia. Inertia is described as the tendency for an object at rest to remain at rest until a force acts upon the object. The same goes for an object in motion. In terms of the tablecloth trick, inertia is important because according to the law, the objects on the table will not move unless an outside force moves them. Initially, all of the objects are at rest. According to Newton's law, objects at rest tend to stay at rest. When we pulled the cloth, friction acts on the objects in the direction of the pull for a short time. The tablecloth is slippery, so these forces are small, and thus the cloth sneaks out from underneath the objects.
For this experiment, I'm going to measure my weight going up and down an elevator and seeing if there's any change. To find the acceleration in an elevator, initial mass must be found first. To find this mass, simply stand on the scale and read the recording in pounds and then convert it to kilograms. When an elevator isn't moving, force normal and force gravity are equal, and the net force is 0. Because the net force is 0, there is no acceleration in the elevator. When going up the elevator, the scale reading changed from 117 to 122 pounds. This is because the apparent weight, or normal force, increases. When going up, the mass and gravitational force remains constant, but force normal increases to 543.45 newtons. You use these new values and plug them into the acceleration equation, which gives you a final acceleration of positive 0.42 meters per second squared. When going down, the scale reading changes from 117 pounds to 112 pounds. This is because the normal force is decreasing. When going down, the mass and gravitational force remain constant, but normal force decreases to 498.09 newtons. You plug these values into the acceleration equation, and this leaves you with a final acceleration of negative 0.26 meters per second squared. Overall, when going up, the apparent weight increases because the net force and the acceleration are positive. When going down, the apparent weight decreases because the net force is negative and the acceleration is negative.
In this short experiment, we will attempt to explain how time is what determines the force, not force which determines the time. By dropping an egg on a concrete surface, the time was recorded as 0.85 seconds. However, the egg dropped in the water was clocked at an even 1 second. Therefore, as the momentum, which is mass times velocity, the two factors that do not change, remains consistent between the two, the impulse changes. This is due to a change in force, which is due to a change in the time of impact. The momentum for both eggs was calculated to be 0.32 kilograms times meters per second. However, the force for the concrete egg was found to be 0.38 newtons, while the force for the water egg was calculated to be 0.32 newtons. It is clear that the single difference between the two eggs is their force, which is due to the amount of time it took for the impact. Finally, it is thus proven that time is the determining factor, not force. And finally, we have this impulse momentum theorem concept visually represented in an artistic poster, courtesy of Elena Quinones.